So in this webinar, we want to go one step further. We're going to again work with a slightly more complicated robot. We're going to add 2 servo motors, as we discussed. We're going to add a slightly more sophisticated behavior. So let's talk a little bit about some different pieces of this puzzle. We're going to start with the servo motors. Then we're going to talk about the concept of a sub-VI. We'll go into a little bit of detail about a specific one we're going to use in this case. We're going to talk about a new structure, which is the for loop. And then we're going to create some autonomous code for this new arm and gripper robot that we're creating. So, servo motors. Here's a nice, long, detailed description. A servo is an automatic device that uses an error-sensing feedback to correct the performance of the mechanism. And here's the short form. It goes to a position and it stays there. So the function, the servos that are included for use with Tetrix, there's 2 types. What we're going to use in this case is the 180-degree servo motor. So this is a servo motor that's got a limited range. The alternate choice is a continuously rotating servo motor, but that's not what we're going to use in this case. So then, as the name implies, a 180-degree servo motor only has a certain range of motion. It does not have the ability to continuously rotate. And when we send a command to a servo, we're actually giving it a value between 0 and 255. And 0 corresponds to the angular position of 0, and 255 corresponds to a position of 180. So there's a little bit of careful thought and a little bit of math sometimes that has to go in to choose your positions. But as we'll see, the schematic editor provides the ability to test and set up these angles really, really simply. So the benefits of servo motors are they're very precise, and that makes them really useful in a lot of robotics applications. So as mentioned, in this case we're going to use 2 servos to control this robot. One is going to control the arm to raise it and lower it, and the second is going to control the gripper to open and close it. So I'm going to jump back into LabVIEW and show you how to configure and choose these servos. So we're going to close this code now that we've reviewed it. Don't need to save any changes. We're going to open our schematic editor, and as Greg showed us a moment ago, and we referred to last week, the servo controller is connected to the daisy chain port of the DC motor controller. And once we've got that servo controller in place, we have the ability to specify up to 6 individual servos and also to attach something else to its daisy chain port. But for now, all we're going to do is select one servo for servo port 1. When we click on the arrow, we can choose whether it's the 180 degree or the continuous. We'll choose the 180 degree servo. And once we've done that, again, we've got the capability of specifying and labeling the motor, which is critically important. So we're going to call our first motor our gripper. And the behavior of this motor is at one extreme, the gripper is going to be open. At the opposite extreme, the gripper is going to be closed. And what we have here within the testing capability of the schematic editor is the ability to choose a position and then enable the robot to actually go to that position. This is a great place to do some testing and to write down and record the positions that you need. So as mentioned, the 0 position is 0, the 180 degree position is a value of 255. You've got that ability to choose those values from this slider here. And it's a great way to test and choose your positions. So we don't have a robot connected right now. There's not really any value because you can't see it. But in our testing before, we learned that for the gripper, the open position was 200 and the closed position was 80. That was the positions that we needed to do the actions that we required. So that's a great place to test that stuff out, jot it down for use within the program, just like I'm going to do now. And in servo port number 2, I'm going to add a second 180 degree servo. I'm going to call this guy arm. And again, set your positions, check them. And in this case, the downward position of our arm is a value of 190, and an upward position is of 25. So that's just some data points that we're going to remember when we're writing our code. So we're going to save and then close our schematic editor now that we've set this stuff up. So the next piece of the puzzle that we're going to need to complete this activity is a for loop. Now, we discussed loops before, and for loops are very similar to while loops. The difference is that where a while loop runs until a condition is true or false, a for loop is generally used to run a specific number of times. So you see there's a terminal here with an N in it. So you would wire a number into that to specify how many times to run. And then what will happen is the subdiagram, the code inside, will run that many times. And there's another terminal inside the loop called the iteration terminal. And that returns the value of how many times the loop has already run. So the first time through the loop, the value from the iteration terminal is 0. This is the single most important thing to remember about for loops, and the single biggest stumbling block is to remember that the term is 0 indexed. So the first time through the loop, the value of your iteration terminal is 0. And as you're going to see when we write this code, we're going to take advantage of that iteration terminal to smoothly move our servos. So the benefit of using servos in conjunction with for loops is that the behavior of servos is to go to a specific angle and stay there. You don't have to worry about it. You give them an angle and it goes there. But sometimes you don't want it to go there immediately. Sometimes you want to slowly move to a position. So what we're going to do in this code is we're going to use the for loop with the servo move command inside it and a short delay to allow us to ramp the motors into a position. And we're going to do that by making use of the iteration terminal. And you'll see that in a couple minutes. Next, we're going to talk about the concept of a sub-VI. Sub-VI kind of is, the meaning is kind of self-explanatory. It's a part of a VI. And really, when sub-VIs are used, it's the way of putting a VI inside of another VI. And it's a way for you to replicate code and use it in multiple places. In this case, the sub-VI that we're going to use is one called the screen update sub-VI. And the purpose of this guy is to write some values onto the NXT screen. It's a great diagnostic tool that shows you the current readings of the ultrasonic sensor and of the light sensor. And the other thing it does, since you've got the ability to reuse this code over and over again, is it also gives you out the numeric values from those sensors. So this particular sub-VI is used all the way through the Tetrix Getting Started guide. So that material, which we pointed to already, takes wide use of this sub-VI that was created for it. And it can be found inside those project files. So let's jump into LabVIEW really quickly just to take a look at this guy. So we're back in our Robot Project Center. We see our sub-VI here under our programs. If we double click on it to open it, I just want to quickly go through it because it uses some functions that we haven't seen before, and they're particularly important to understand. So we see here that we've got, for the first time, we're caring a little bit about the front panel of our code. Right here we're looking at the block diagram. But if we jump to the other part of the code called the front panel, we see that we've got some controls on the left-hand side and some indicators here. So if you look at the left-hand side, which are the inputs, we've got our NXT terminal, and we've got two string controls to allow us to specify what text we want to display in line 5 and then in line 6. And then on the right-hand side, which are the indicators, or the outputs of the sub-VI, you see that we've got another NXT terminal, and we've got two numeric indicators, one for the sonar distance and one for the light sensor value. So what's going to happen is that this sub-VI, which you see has an icon here, and if I use our handy-dandy Control-H to bring up our context help, has been defined to have inputs on the left, outputs on the right, and to be used within other code. And that's exactly how we're going to use it. However, let's talk about how it works first. So we're going to leave the front panel and go back to the block diagram. Just take a look at the functions and follow it through. So the first function we see here, taking in the NXT terminal value, if I bring back up my context help, is the read light value, read light function. So it's connecting to port 3 and it's reading out a numeric value from the light sensor. If we follow that output, which is along this blue wire, and the blue wire indicates that it's an integer value or a whole number, we see that it then comes into a function here called NXT number to string. So the purpose of this is to take this number and display it on the front of the NXT brick. So in order to do that, we can't just display a numeric value, we have to convert it to a text value. So that's exactly this function. And if you need to access this function yourself, you can bring it up from the functions palette, NXT-IO, and then display control. And when you place this guy down, we'll just do it quickly and then remove it. You've got all kinds of choices here between write, draw, and erase. Oops, sorry, I jumped to the wrong function here. That's it. I jumped ahead. So the actual function that we want is in NXT-IO It's hiding from me. NXT programming, string and number conversion, and then NXT number to string. So it's a little bit buried there, but it's a useful function. So if you want to jot down how to get at it, you can see it befuddled me for a moment as well. So it's a good one to be able to pull up and use. Next, once that's converted to a string, we just need to combine that with a little bit of a label to explain what's going on. And this is using the concatenate string function, which is again NXT programming, and then underneath string, we've got concatenate strings. What that does is just combine these two strings together to give a more detailed explanation into the NXT display. So we've got a second sensor read here. This one is set for ultrasonic, so it's very similar to the light sensor read. A number is coming out, being converted to a string, and having the words sonar value appended to the front of it. And then both of those are going to the same function, the one that I just pulled up, which allows you to write to a specific line of the NXT display. So it's writing the light value to the first line, the sonar value to the third line, and then whatever strings have been written to the inputs of our sub-VI get displayed in the fifth and the sixth. So you can see why this is a little bit complicated, but not too bad. But this isn't the kind of code you want to have to write over and over and over again. So it's a perfect candidate to place within a sub-VI. And hey, since we're already using it to read the light sensor values and put that into a string, why not also output it? And that's the reason for spitting it out the right-hand side of the function. So we're going to close this guy now, and we'll see how it's used in a moment. Not save any of my changes.